Hey, welcome back everyone. I just wanted to get a little bit more technical on the subject of the capacitors. We saw from a previous video that they're pretty simple in DC circuits, but when you subject them to AC or alternating currents, the behavior of capacitors can get a little bit more complicated, but fortunately it's all very predictable. Now in AC circuits, we tend to gravitate towards that 60 Hertz alternating current that comes out of the wall outlets. That's great for power delivery when we run those large voltage devices, but alternating current can show up in lots of different applications. Alternating current can show up when it's interference from digital signals, where it can be in the tens, hundreds, thousands, or even millions of hertz. Hertz means alternations per second. So millions of alternations per second we would refer to as megahertz, kilohertz. Radio waves often travel in kilohertz and megahertz. Audio signals, those have oscillation frequencies of anywhere from usually the tens and 20s of hertz all the way up into tens, 20s, thousands of hertz. So those alternating current signals can behave drastically differently based on what frequency we're dealing with. And we could think of DC voltage as alternating with a frequency of 0. So all the math that goes into AC circuits would still apply in DC circuits, but we usually kind of ignore it because the frequency is 0, and in a lot of equations, you plug in a 0 and a lot of things cancel out. Now, the main fundamental formula that we use for frequency implications in alternating circuits, we refer to as this concept called reactance. Now, in a resistive circuit, where our circuit is just built out of resistors, those resistors do nothing but limit the flow of electricity. That's their job. So we refer to them as resistors, and the value of the amount of current that they block is resistance. Well, when we alternate electricity in a capacitor, the slower we alternate that frequency, the longer it has to be able to build up that charge. And back from the capacitor video, we saw that if we built up charge for long enough, current would stop flowing altogether. So if we have a very low frequency, very slow alternation circuit, we expect that charge to build up, and on average over a period of time, we really aren't going to let through that much current. So we would say that the resistance is very high. The opposite effect, if it's alternating very quickly, we're pretty much always at that initial stage of allowing through a lot of current at the very beginning of the charge cycle. Since we're alternating so quickly, we never get that chance to build up any charge, therefore we never get the chance to limit the flow of electricity. Or we would say that the resistance is very low. A lot of current can pass through. Now, since it's not a resistor, we can't really recycle the word resistance because it's reserved for the component resistors. So we have a term that's called reactance. Reactance is the concept of resistance to the flow of electricity as it applies to the capacitor and also to the inductor, which both respond to the frequency. Now, it's not just frequency alone, but when we think of the creation of of alternating current, it would be in a form similar to what they call a generator. A generator is a complete revolution or rotating one full rotation. And if it's done in a matter of seconds or fractions of a second, the hertz, the frequency, refers to the number of full revolutions in 1 second. But another concept is called angular velocity, and it's really how far around did we have to travel to complete a full circle. Now, if it's degrees, we would say that that full circle consisted of 360 degrees, or 360 degrees per revolution, or degrees per second. But in most terms, we refer to this unit that doesn't really have a unit. It's referred to as radians. You may have heard of that in trigonometric applications. Some calculators by default work in radians. The distance around a full circle, the circumference of a circle, is 2 pi times the radius. Now, if that radius is any real given unit, I'll have other videos to explain this a little further in depth, we would say that to go 1 full revolution, it takes 2 pi radians to go around per full revolution. If that's done in a matter of seconds, we multiply it by that frequency. So we would say that 2 times pi times frequency is how fast it's rotating around that full circle. So when we add that 2 times pi times frequency element into the situation, we also have to take into consideration the size of the capacitor, the amount of capacitance, and both of those put together will tell us how much resistance the circuit is going to see to the flow of current. Now, as the frequency gets slower and slower and slower, we're charging up that capacitor, so our resistance is going to get higher and higher and higher. We call that an inverse relationship. As frequency goes down, resistance goes up. But the same with the capacitor. Think of the capacitor as a large capacity bucket. If that bucket is huge, it's going to take a long time to begin to fill. So the bigger the capacitance, the longer it would take to fill, and the less resistance we're going to see. Large value capacitor, small value of resistance. That's another inverse relationship. Both of these are inverse relationships in terms of capacitance. So if we're going to talk about how much resistance we see to the flow of electricity in a capacitive circuit, we say the capacitive reactance, or X is the abbreviation they give to it in electronics terms, is equal to 1 divided by 2 times pi times frequency, there's that angular velocity consideration, and capacitance, 1 divided by 2 times pi times F times C. Both the frequency and capacitance are on the bottom of the fraction. That means as we change one of those elements, or both of those elements, increase or decrease it, the exact opposite will happen with the resistance of that component in the circuit. Since the resistance going up or down would cause the current to go down or up, again, the opposite effect, then that means that an increase of frequency leads to an increase of current. An increase in capacitance leads to an increase in current in your circuit as well. Now, often there's a resistor and a lot of times an inductor in the circuit as well. So we may see some counter effects, but if we're just dealing with the capacitor alone, then those properties will remain intact. So capacitive reactance, the effective resistance to the flow of electricity, is equal to 1 divided by 2 times pi times frequency times capacitance. Change either one of those elements, and the opposite change will be seen to the reactance, or the effective resistance that that capacitor is exhibiting into the circuit. That allows us to use the frequency changes to actually change the properties of our circuit. For example, we can allow a signal to pass through a circuit if a higher or a lower frequency happens to be coming through. We might refer to that oftentimes as a filter circuit, where a higher or lower frequency than our particular value that we want, higher and lower frequencies can be either allowed through the circuit or blocked by this capacitor. They can also have effects of separating an AC and a DC signal. Sometimes we have a DC signal in an amplifier to effectively turn it on or give us an amplification amount, but we don't want to see that DC signal coming out at the other end. We only want to see the AC signal. A capacitor is a great way to block the DC signal because it blocks any component that's DC because the resistance is extremely high. But the AC component of the circuit, since it's alternating, allows the current to pass through. So we can separate the AC from the DC components of a circuit if we have those two components we call coupled on top of each other. So great for filters, great for coupling, and far others, more subjects as well, but that's just a couple of the examples of things that we can use these capacitors for and their property of changing resistance as the frequency and also the capacitance can be changed. So definitely more to come, but that's just a little bit of a taste of how we can use the capacitance and the frequency to predict that response that the capacitor is going to have in a circuit. Thanks for watching.